incredible, digital technology that's able to do these corrections. And this is actually the, I want to say it's Gemini, but Gemini should be 2 or maybe they just count. I think it's Gemini telescope, but this particular one is in Chile. And if we look at the same source without adaptive optics versus with adaptive optics, look at the difference in resolution. The box here is 5 arc seconds across. The field of view is 5 arc seconds across. So here you can see that the angular resolution is about 1 arc second or so. It would be 5 pixels across the box. That's sort of like what we're seeing here. That's the native resolution. If we just look through the atmosphere, we don't do anything fancy, we're going to see that resolution with this telescope. But when we go to the adaptive optics, now all of a sudden you see the pixels here are much, much smaller than 1 arc second. They're probably on the order of around 100th of an arc second or something like that. And you're seeing details in that star cluster on the right that you have no right to see from the surface of the Earth. You wouldn't ordinarily be able to do that. It's only because of the adaptive optics that we're able to do that. All right, so anyway, we still really haven't gotten to non-optical telescopes yet, although some of the concepts we just discussed we're going to carry over in the second part of the lecture where we talk about non-optical telescopes. The reason I'm showing this is because, again, I want to emphasize the fact that when you're talking about optical telescopes, you're just talking about observations in that little itty-bitty range where we can make human observations directly with our eye, where the visible light range is. Yeah? I mean, as Carl Sagan says in one of his cosmos things, there's kind of a chauvinism about that, like it's special, because that's what we're directly able to see with our eyes. But the simple reason for that is because that's what sunlight is predominantly made of. That's the most prevalent kind of light on Earth. So, we've evolved from most other creatures to use that light. But there is kind of a chauvinism about it. There's nothing special about that wavelength thing. It's just what we're able to see directly. But there's all kinds of other wavelengths being produced by astronomical objects. Longer waves, infrared, microwave, radio down there, and shorter waves, ultraviolet X-ray, gamma rays, which we've already talked about. And different objects produce these different wavelengths. So if we're talking about a supernova explosion, it's going to produce gamma rays and X-rays. There's going to be some visible light, but most of the energy actually comes out of gamma rays and X-rays. These bodies have such high temperatures. Remember, by Wien's law, there's a connection with temperature. So stars have temperatures around 5,000 to 10,000 Kelvin. But when you're talking about massive astrophysical explosions, then you're talking about hundreds of millions of Kelvin. And we really wouldn't learn much about this. We weren't able to make observations from these other wavelength ranges again. So the sky looks like X-rays, the sky looks like radio waves, which we're going to talk about. This is, of course, the galaxy looks like optical. So, there's clearly, just because these images look so different from each other, just immediately tells you there's very different physical objects involved in creating these different kinds of emissions. And suppose we could only see this. If we only saw that, we really wouldn't have ever had a clue that black holes were out there and other exotic things. And those things are not merely of academic interest, because now we're starting to understand that the whole universe, in a way, is kind of an ecological system, and you need all these different things. You probably need black holes, and you need supernova explosions to get life on them. You really do, because the heavy metals that are in our bodies right now actually were developed in the cores of massive stars that went supernova. You can't get to some of the more dense elements beyond iron if you don't have a supernova explosion. It's the only way they even get created. So, as another thing Carl Sagan says, is that we are made of star stuff. But as weird as that sounds, it's actually true. The heavier elements in our bodies actually just didn't get here by any natural process on Earth. They came from the cores of exploding supernova stars hundreds of millions or billions or billions of years ago. And again, if we could only be looking in the optical range, we wouldn't know anything about these processes that are not merely, again, of interest to just astronomers or interest to anybody who's interested in life in our galaxy, the universe. All right, I've already discussed a little bit about atmospheric blockage, but we kind of get into that again here. Now we're talking about making observations at non-optical wavelengths. So if you're talking about the atmosphere as acting like a filter, then there's only certain wavelengths that actually make it through the atmosphere. You have the optical window, of course. We look up, we see beautiful glowing yellowish sun. Well, that's because those waves pass through the atmosphere, through the windows, in that wavelength. There's also a window in a certain part of the radio wave spectrum. But energy emission from space generally gets absorbed by the atmosphere. Microwave gets absorbed by the atmosphere, and longer wavelength radio emission gets absorbed by the atmosphere. So there's certain kinds of astronomy that we can't do from the surface of the Earth. This has nothing to do with that resolution thing I was talking about. This is just flat out absorption that the atmosphere does. It simply absorbs some of these wavelengths. So, a different way of looking at it, if we kind of plot mathematically how much absorption there is, there's like 100% absorption in this microwave region right here. Right, 100% in this radio region, but there's a window right there and a window here in the optical. And of course, what the radio window means is that we can do radio astronomy from the surface of the Earth. So if we have big radio telescopes, we can put them on the Earth and make observations, and we can communicate. So this is the basis for radio communications for astronomers. If that window weren't there, we actually could only communicate with astronomers basically by going out and flashing mirrors at them. We have to use optical radiation only. All right, so the specific ways in which we have this kind of blockage taking place are a little different for different wavelength ranges. The radio waves of longer wavelengths are actually reflected by the ionosphere. So we'll see when we talk about Earth's atmosphere that there's a layer way up about 100 kilometers up in the atmosphere or so that's so high up in our atmosphere that solar radiation causes atoms to split up and become ionized. They lose electrons, as we talked about. And when you get plasma, like we have up there in the ionosphere, you have electrons and positively charged ions. Well, those are charged particles, and they interact with radio waves in such a way that they act sort of like a mirror. So radio waves from the surface of the Earth don't penetrate the ionosphere, and those coming from space don't penetrate the ionosphere either. Microwaves are blocked for different reasons. Microwaves and infrared are basically absorbed by water molecules. Again, this is basically the principle of microwave ovens. Microwaves are absorbed by water. That's the reason that your food heats up in the microwave. All our food has some water content, and it absorbs microwave radiation. The higher energy forms, ultraviolet and X-ray and gamma ray, are blocked predominantly by the ozone layer, which is another layer that also is pretty high up in the atmosphere. Okay, so if we want to make observations of some of these wavelengths, we actually have to do it off Earth's surface. So we can use, for example, here, this is something called the Compton Gamma Ray Telescope right here, which is observing gamma rays from space. And then on the right-hand side is something called CERTIF, which is an infrared observatory in space, a couple of NASA's great observatories in space. All right, so what can X-rays and gamma rays teach us about the universe? Well, they're very high energy forms of radiation. So as I showed you when we had that thermometer plot, we're talking about temperatures above 100 million Kelvin, around about 100 million Fahrenheit. Those are blocked by our atmosphere. And it's probably no coincidence that they're blocked by our atmosphere, because if they weren't blocked by our atmosphere, we probably wouldn't be here right now, because those high energy forms of radiation are also very detrimental to living cells and DNA and stuff like that. So again, Earth's protective layer there is really helping us. But the origin of that emission in space is very high for objects which typically involve very compact and massive objects, like neutrons and black holes, where we have gas that's attracted by the strong gravitational field. And if you imagine gas just zooming straight for the small object, if all the gas zooms straight for the small object, the gas gets closer and closer to its neighbors, and that compression leads to heating. And that's why we actually get the heating that we get, the high temperatures that I'm talking about here. It's because of the incredible compression that occurs. In the case of a black hole, you get this compression just before the matter crosses the event horizon and doesn't even see anything. So this is just an artist's conception. We have no way of actually directly seeing the flows of matter around a black hole, but we think they form into disks like this, because most matter has a certain amount of rotation to it anywhere in the universe. And when this matter that has some rotation to it gets attracted to something like a black hole, it actually just doesn't fall radially straight in like a falling rock. It tends to actually go into orbit and then slowly spiral in. And we see plenty of evidence for outflows of matter too, from near black holes and even some other compact objects. So this is an animation. That was really good. Anyway, sorry, my laptop will switch here. Okay, good. All right, so about hydrogen astronomy, we also have, as you'll see next semester, frequently in binary systems we can have a normal star like the sun, but in orbit around a kind of freakishly dense object like a black hole or neutron star. And what happens is when you have a compact object like that, it tends to, well, suck the life out of the other object. It's not really a very nice way to put that. It just kind of unceremoniously yanks the atmosphere off of its neighboring star. These objects are actually in orbit around each other. You'd think that this would be the dominant object, but they have about the same amount of mass. It's just that one is so compact. But it's just as much mass, so they actually kind of orbit around each other in a pattern like this. But matter is being pulled off the normal star and actually goes to the orbit around the black hole. In this case, the black hole. And as it falls in, it gets superheated, like I was saying, because of the compression, and its final stream is in the form of X-rays, usually. So this X-ray emission that we actually see is due to the final compression that takes place. Let me just keep moving on this to see if I actually can pull this up. Really probably can't